So welcome to the last talk of the conference. So my name is Daniel Jaque from Universidad Autónoma de Madrid, and it's a pleasure to introduce Luis Carlos from Portugal. I think there is no need to say too much about Luis Carlos. Just a funny thing, I was just talking to one student from Portugal, and then I asked the student, so where are you from? He said, I'm working in Portugal, but I'm not in the group of Luis Carlos, you know? So they said, okay. So that clarification was nice. So everybody knows Carlos, so things I think to say is you are so important in the field that instead of one chairman, you are going to have two chairmen, okay? Because one chairman is not enough, and I apologize because I need to leave to take the plane, so I will miss half of your talk. So nothing. So just before the talk from Luis Carlos, I will just to remind you that very soon you will get an email from the International Conference of Luminescence, ICL, that will be celebrated in Kyoto, in Japan, next year, last week of September. So all of you will be invited to participate. So I will hope to see all of you there in Kyoto. It's not going to be as Tenerife, because things that are done in Spain is impossible to make as good as in Spain. Everybody knows that, but and especially by Jorge. But I hope we will do a very nice conference, fundraising conference. So thank you, Luis Carlos. Your turn.
Thank you.
And the speaker for the questions, the chairman for his question will be Fiore.
Okay, so thank you. I am so honored by have two chairs, so this is the first time. Okay, so first I'd like to thank the invitation, but I have a small surprise for the boss, so I will keep more words to the end of the conference, okay? So I will talk about water, okay, and a density dance, and I'd like to start with a story, okay? So this is the speech that David Wallace gave in the 2005 in the US, and the title of the speech, look, this is water, okay? And then the story is the following. Imagine two young fish swimming along, and they met an older fish. Could be the opposite, okay? Two older fish met a smaller one. It doesn't matter. And then the old guy said, "Mon boys, how's the water?" Look at the answer. The two young fish swimming on for a bite, and one of them looks over at the other and asks, "What the hell is water?" So, of course, it's a story, again, unconsciously, and about how we many times do not give importance to the small things that are surrounding us, which are really, really the most important. But for us here, water is that reality. Why? Because it covers our planet, fills our cells, shapes biological and chemical processes. So it's very familiar, but it's not simple at all, okay? So beneath the surface, it is restless, fluctuating, and full of hidden structure. So my idea today is to try to dive deeper and try to understand what water is, okay? And for that, I will call your attention for looking under the surface, of course, and looking carefully to the choreography of the water molecules, okay? And then we have a well-known dance of water molecules. This video illustrates that. So it is the water ability to form hydrogen bonds, okay, with a very fast dynamic. And this is probably one of the, or only the one converging point concerning the interpretation of the anomalous behavior of water. Why? Because There is, however, a hidden and not so well-known dance in liquid water. Okay? And the motivation for this lecture is to unfold the story of that bridges luminescence thermometry, Brownian velocity, luminescence nanoprobes. Here I will mention two types, proteins, fluorescence proteins, and up-converting nanoparticles, and this intriguing dance in liquid water. Okay, so before starting, I want to give credits to the people in the group that works on this subject, especially to the two PhD students that now are working on that. So Ramon Filho and Yongwei Guo, which is they are here, and also part of the results that I will present were obtained by Fernando Maturi during his PhD thesis. Now Fernando is on Autónoma in Madrid in the first chairman group, the first chairman of this talk. And okay, I should also give a strong emphasis to the work of Carlos Bridge on this subject. Okay, so the outline is this one. So first I will talk a little bit about the anomalies of liquid water, okay, and then the model that in our present days can be used to explain these anomalies. Then I make the bridge to that hidden dance, and on the final part of the talk I will, present our results with fluorescence proteins and up-converting nanoparticles, trying to demonstrate that we can use the luminescence features to extract information about this hidden dance. Okay, so anomalies in liquid water. Okay, water is familiar, as I mentioned. It is simultaneously the most common molecular substance and the weirdest of all known liquids. Okay, so there are several thermodynamic, dynamic, and structural anomalous properties. What people means here by anomalous? If they compare water with other liquids, okay, so the behavior of water is, in many cases, completely different. Okay, so this is why people call anomalous properties of water. Okay, so just to be brief on this point, at least 66 properties differ from most liquids. Okay, you can, if you are interested on that, you can follow this website, which is managed by Martin Chaplin in London, in which there is a detailed description of all of these properties that are different than the other liquids. Just to give you two examples, okay? One here. So this is due to the surface tension of water that it is possible to have these water striders walk on water, okay? Also, this picture here illustrates completely different properties of water comparing to other liquids, which is the solid phase is denser. Okay, so the contrary to other normal liquids, which become increasing denser as they get colder, water reaches its maximum density at about 4 degrees. Okay, and this is, for instance, fundamental for life in oceans, especially in the winter, in which the surface of the lakes are frozen. Okay, but the point that I want to emphasize is that one. A full understanding of the dynamic and structural properties of water is still missing. Let me ask some help from two guys that are really experts on this subject. Okay, first, Philip Ball. Look what Philip said about the understanding of water. So it's still a mystery. Worse, the more we look, the more the problems accumulate. Okay, but you can say, this is in 2008, so 20 years ago, so now the things are completely different. We have instruments, people much smart. I'm not sure. Look what Alan Soper emphasized 8 years ago. So many decades of research have been devoted to the study of pure water and its interactions with salts, solutes, and surfaces. But simple questions like, what is water? Why is water like it is? Still elude us. Okay, so one model that in recent years becomes more likely to try to explain these anomalous properties is this two states model. Okay, in fact, we have theoretical and experimental results on the last five years that support the existence of a liquid critical point here in the supercooled region of the water phase, that diagram, okay? And this critical point separates one region in which the low density liquid dominates with patches, with domains of high density liquid, from another region in which we have the opposite. So, high density liquid is the dominating phase, and then we have patches, we have domains of the low density one. Okay, so it's more or less like the coexistence of two emission liquids that are separated by a thin interface similar to the oil-water coexistence. Okay, so in the supercooled region, we can describe the two phases by this local structure. So the low density liquid is essentially a tetrahedral arrangement of the water molecules, while the high density liquid is much more organized. So there is a disruption of this tetrahedral state. And in one case, it's much less dense than the other, and the difference on density was estimated, not really measured, but estimated by several simulations that is around 20%. Okay, so, but what happens at room temperature? So we can think that, okay, we are very far from that liquid-liquid transition in terms of temperature, but that fluctuations between low density and high density motifs, low density and high density domains, can extend in such a way that at room temperature we can define some kind of transition temperature. Okay, what it means that below this crossover temperature Tc, we have the high density regions, which is the dominant phase, okay, and then in that high density liquid we have domains of low density phase, okay, and above this crossover temperature the low density motifs vanish, okay, and we have only one local structure of the hydrogen bonds, okay? But I should emphasize that this still to be controversial, okay? We received very recently a review report of one of our papers saying that I do not believe on this scenario, okay? But, okay, you can ask, okay, but this is a new thing, thinking water as the mixture of two liquids. Not really. Look, 1892, there was the first suggestion that hydrogen bonding is the important key in the water description, and then water can contain microscopic icebergs. Okay, so this is an idea that was in the literature since long time ago. The key point is that to experimentally have evidence of this coexistence. Okay, so we can have a picture of these fluctuations. This is a molecular dynamics simulations performing above the window line, in which the high density motifs in red dominates, and you can see the fluctuation between low density and high density. I give a strong suggestion, people that are interested on this subject. This film here is about 1 hour time duration. Is very, very nice movie describing water structure, water properties in a very, very professional way. Okay, so now let's me to try to make this more clear. So I hope so. So let's me use this painting here, which is the dance at Le Moulin de la Galette, de Renoir, and to give an analogy between the dance in liquid water and the painting, okay? So the painting depicts a crowded dance restaurant, okay? Le Moulin de la Galette. And then some customers, see here, are seated at large tables, taking up significant space as exactly the tetrahedral structures in liquid water. But others, you know, others are dance. So they move rhythmically in synchronism with the music, like the densely packed disorder regions in water. Okay, but just that as heat excites water molecules, okay, the dancers can be moved faster or slowly depending on the tempo of the music. Okay, but this is a very dynamic situation. Okay, this is like the painting is it describes a lively scene. So there is a constant exchange. So occasionally some of the dancers decide to rest a little bit, while others decide to join the dancer. Okay, and this is exactly what we have when we are describing water. Moreover, when the dance floor becomes overcrowded, tables might be moved to create more space, just as the structure of water adjusts to accommodate more high density domains. Okay? Conversely, when the energy in the room decreases, more tables might reappear, symbolizing the return of the low density patches. So, also, the music genre, so at that time, not rock and roll, of course, is jazz or swing or classic music. So it acts as the governing force that drives the dynamic of the dancers and of the people illustrating in the painting, exactly as the fluctuations between low density and high density motifs are orchestrated by the water's inherent properties like temperature, pH, ionic strength, so on. Okay, so I think that I was able to illustrate that presence of these two different structures. Let's see how we can use concepts like Brownian motion and fluorescence proteins in this first example to study these fluctuations between high density and low density domains. But first, let me call attention to one very important thing. It is very well known that hydration is a fundamental key for the function of proteins, okay? So the dehydrated protein in general are not active. So, and we can see this here in this a quote from this paper here. So dry proteins exhibit no biological activity and require at least a water monolayer, okay? People call this the hydration shell, okay? And I will use this concept in the rest of the talk. Okay, so the question comes, can in some way connect the folding and unfolding process of a fluorescence protein with the anomalous properties of liquid water? Why? Because the conditions that we are working, that aqueous suspensions, okay, in which we have a probe in water, the movement of the probe is linked to the movement of the water molecules that's surrounding the probe, okay? I will show this in numbers in a few slides. So, in fact, there is a cooperative movement of the probe and of the hydration water, okay? So, this is why we can think that maybe the fluorescence or the luminescence features of the probe can give some insights on the hydration water. Okay, so for that, we need to use luminescence thermometry. So I use here a nice picture from Ricardo Marin. So, and okay, I think that everybody knows the fundamental of the method. So essentially, we are using a remote detection method based on the temperature dependence of luminescence features. So we have several of these features that change when we change temperature, but here we will use two of them. So in the fluorescence protein, we will use essentially a peak shift, and in the up-converting nanoparticles example, we use the ratio between the integrated intensity of two bands. Okay, so if you are interested on more details, I benchmark here a little bit our work in cooperation with Dani Iac, Ervin Ximendes, Ricardo Marin, Marcos Schutt, and Carlos Brits and Albano in Aveiro. Okay, so next important point is the Brownian motion. Okay, so the point here that I want to emphasize is that Brownian motion is essentially a thermal motion driven by the interaction between the solvent molecules and the probes. Okay, so we use this idea. Okay, and with this very important point, which is in the conditions that we are working in terms of concentration of the probes, we are in a regime, okay, in which the hydration water, okay, so remember the layer of water molecules that's surrounding the probes, is considered part of the nanoprobe. Okay, so when we are studying, for instance, in the up-converting nanoparticles, we have a charged surface, okay, and then the interaction between the water molecules that belong of this hydration water with the charged surface will be very important. Okay, so first part of our results. Okay, these are the work of Yongei Wang. Okay, it's PhD. So in the first paper, we measure the Brownian velocity of an enhanced green fluorescence protein essentially is a modification of the well-known green fluorescence protein suspended in water, okay? And in brief, now recently we extend the measurements in a range that can englobate that crossover temperature that I mentioned before between the low density and high density domains. Okay? So let me summarize the fluorescence protein, the fluorescence properties of the enhanced green fluorescence protein. So this is the emission spectra at different temperatures, 2 different temperatures. You can see that there is a peak shift as temperature increases. Okay, and then we can check this in more detail. In fact, there are several parameters that change with temperature. So the peak 1 energy, peak 2 energy, the full width at half maximum of these 2 peaks, the relative intensity of them. But yeah, for the purpose that I want to stress here, we use the most simplest approach, which is simply check the energy of the main peak as a function of temperature, okay? And then we have this nice calibration curve that permits to convert energy of the peak in temperature. Okay, so we measure the Brownian velocity of the protein in water. I will not enter into the details of the method, okay? But one important thing is, okay, how your results compare with literature ones, because you are using a new method to measure the velocity. First, we will see that there is a decrease of the Brownian velocity when we increase concentration, okay? And this is attributed to protein-protein interaction. But then when we compare our results with the very few results in literature using a completely different method to measure the Brownian velocity of the same protein, okay, we see that these values are literature values. They are obtained at different concentrations comparing to our, but all the values, these are our 3 points, and these 2 of literature matches well what we expected. Okay, so we are confident that our method can be useful for that. So next, we extend the concentration range, okay, and we got this very nice trend here. So you see these 3 points are the points of the first paper. Then in this second paper we have much more points. We have that same linear tendency, but apparently for high concentration the Brownian velocity reaches saturation, and we do not have yet an explanation for that. So this is probably, I hope, the subject of future studies. But okay, now what is, yeah, we demonstrate the measurement of the Brownian velocity at room temperature, but remember, our intention is to check if we can sense that transition, that crossover temperature between low density and high density. So for that, we need to measure Brownian motion, Brownian motion as a function of temperature. Yeah, these are the results. Okay, look here. Between room temperature and almost 70, so we found for different concentrations, okay, always bilinear behavior. Okay, so, and the crossover between these 2 regions, it's what we call crossover temperature, and then we can say that below TC, so in this region here, so the transient low density domains exist, okay? in the sea or within the predominant high density phase, and then this increase the effective hydrodynamic mass, okay, the protein plus the hydration shell, and it is the reason why the Brownian velocity here in this part is lower than there, in which we have only the high density regions. Of course, above TC, there is any more low density motifs, and then water becomes more structurally homogeneous, which enhance the protein mobility. A very interesting thing, which is different than what we will observe later on when we put nanoparticles in water, okay? But for the fluorescence protein, there is no variation of the crossover temperature with the concentration in this concentration range, of course. So it is consistently measured around 55, okay, which is an indication that this bilinear behavior arises from the solvent structure rather than from the interaction between the proteins, okay? And also a very nice result is that when we compare this value for the crossover temperature when results that exist in the literature for other proteins, our value matches closely the results of other groups. Okay, but remember, the idea was to use this to study the protein unfolding process. So, both experimental and theoretical studies have highlighted the role of hydrogen bonding in protein stability, and there is I can say, a very controversial assumption, which is the following. This was proposed by Malamas, not so far in time, which is the following. So the idea is that the protein unfolding begins at a temperature which is coincident with that crossover temperature between low density and high density domains. So in other words, what Malamas proposed is the following. If we do not have low density domains, the protein starts to unfold. Okay, and this is really, really interesting because think that temperature is around 45, 50 degrees, which is more or less the temperature at which life starts. So people know that it is for life we need to have temperatures on that area. Okay, so this is why some people speculate that there is here a fingerprint much more important than that apparent is. Okay, but I don't want to enter on this. This is really for me very thin ice, so I don't want to walk on these regions. But the point is that could we use our data to give some insights on this idea? Okay, so this is the question. Then the first thing that we realize is, okay, let's compare the onset of protein unfolding, and we can do this measuring the fluorescence quenching as a function of temperature. So let's compare this with that crossover temperature that we measure from the Brownian velocity temperature dependence. Okay? So, Yongwei comes to the lab several days working with this idea. Okay, so let's perform heating-cooling cycles, okay, in which the maximum temperature is increasing between room temperature essentially and 95. What we observe is the following. So up to a certain temperature, we recover all the initial intensity, okay? And this is a fingerprint that after the unfolding process, that process is reversible or is entirely reversible. But above a certain temperature, okay, we start to see that we do not recover the initial temperature, okay? And here in this picture, you can see the intensity recovery in percentage as a function of temperature, as a function of the maximum temperature of the cycle, and then you can see in red is the melting temperature of the protein, but this is not what we are interested here. We are interested on this blue arrow that marks the onset of the protein unfolding. Why? Because it is the onset in which the intensity is not entirely recovered. And, sorry, look to the value, okay? That value here is 56, okay, degrees. And the crossover temperature that we measure by the Brownian velocity was 55. Okay, so the two things, the two temperature matches well. Okay, but this, I think it's not enough support, okay, could be a coincidence. So what we did is, okay, we know, because it is very well described in the literature, that the isotopic substitution increases the stability of the protein. Okay, so what we did is the following. So apparently, seems that the protein unfolding requires the presence of this low density motif. So let's prepare suspensions of the same protein at the same concentration, but now using heavy water. Okay, and perform the two things. First, measuring the temperature dependence of the Brownian velocity to check the crossover temperature, and then compare this with the unfolding temperature. And look at the results here. So we confirm the influence of the isotopic substitution. So look, the suspension in heavy water in orange is stable up to larger temperatures comparing to the one in water. And when we went to the lab to measure the Brownian velocity temperature dependence, this is a very, very nice result in which the crossover temperature appears at higher temperatures. And again, the two values matches well. So if it is a coincidence, it's a nice coincidence because two times, okay? When we have these things, so I don't know if we can call them coincidence or not. So, in short, this first part demonstrate or at least support the idea that we have a connection between the presence of the low density domains and the unfolding process in proteins. So this is an example now. I will move to the charged surfaces, okay? And what we did here is the following. So let's use an up-converting nanoparticle in which we know that we have charges at the surface and see how this will impact the measurements of the Brownian velocity. Okay, this is the work of Ramon, the PhD work of Ramon. And we use for that one more example of these particles, which are really, really the most one used in the community. So sodium yttrium fluoride doped with ytterbium erbium, okay? And here we will measure the temperature using the ratio between the two bands of the erbium in the green after excitation of the ytterbium ion in the near infrared. But first, let me say the following. So I will present next several examples of the determination of the crossover temperature in different systems, okay? But all of these crossover temperatures are in this part of the temperature dependence of the isothermal compressibility, which, by the way, is another abnormal property of water comparing to other liquids. And why this is related to density fluctuations? Because isothermal compressibility depends on the volume, okay? And then the density, the two phases have different densities, as I mentioned. So the first example, this bilinear behavior in silver sulfide nanoparticles. Here, people use it a ratio of F intensities. Second example now is the emission peak wavelength of these quantum dots, the same bilinear behavior. Third example is the energy transfer efficiency between particles doped with ytterbium and particles doped with neodymium. Again, bilinear behavior. The two final examples, sodium yttrium fluoride, okay, two particles with different sizes, but here is the Brownian velocity, but in this case, this was performed in Aveiro. We use a method for measuring the Brownian velocity, and this was performed in Madrid using optical tweezers. So the two methods are completely different, but they furnish velocities that make sense considering the different in sizes, and more important, they show this bilinear trend. Okay. An important thing is that changing the systems and changing the methods of measuring the fluorescence property, the luminescence property that we want to study as a function of temperature, we have this range of crossover temperatures. Okay, so the question is why? Why different systems have different crossover temperatures? And then, can we in some way shed some light on this question? Okay, so let's focus on these sodium yttrium fluoride particles, okay? Let's check if there is some size dependence on the crossover temperature. And the answer is yes, starting by this example. Look, here, contrarily to the case of the protein, when we change size between 15 and 100, roughly, the crossover temperature changes, okay? And this work was also done in cooperation with Xiaogang Liu. And you can see here, in short, the dependence of the crossover temperature as a function of the nanoparticle diameter. So there is a size dependence of the crossover temperature. And what about pH? Yeah, we still in the same work performing in Aveiro, and you can see here for 3 different particles, when we increase the pH, the crossover temperature decreases. This pH dependence was also observed in different systems, organic dyes, europium complex, and other up-converting nanoparticles, the ones that were measured in Madrid using the optical tweezers method. And here, there is a very interesting result, okay? There are conflicting results, okay? In Aveiro, we measure that dependence. So the crossover temperature decreases when pH increases. In Madrid, they measure the opposite. So the question, okay, there are several hypotheses for that. The most, easy one is that, okay, the guys at Aveiro are wrong because they don't measure the things correctly. The other is the opposite. So, yeah, it is Madrid that not have sufficient care measuring things. Or maybe pH and temperature, maybe pH and size are not good descriptor for that. Okay, so maybe there are another parameter, another descriptor that can be more useful for that. And yeah, let's think in the effective surface charge density of the nanoparticle, okay? We are not now anymore interested in the pH or in the size. What we are saying here is that changing pH or changing the size is equivalent to change the distribution of charge at the surface of the nanoparticles. And then, if we use this new description for these two examples, we found a master curve. Oh, crazy. You see, all the points, all the sizes, all the pHs, completely different methods. Okay, our method in Aveiro, and which is not so well established, that the optical tweezer method, give the same, they're fall down in the same curve. Wow. But let's try the following. So let's measure two particles with the same size, okay, at the same pH, but with different surface functionalization, and check if this master curve is a coincidence or not. So for that, we use commercial particles, okay, from this company here in Finland. So there are, again, sodium yttrium fluoride particles doped with ytterbium erbium with two different functionalization, okay, carboxyl functionalized groups and azide groups at the surface. So identical sizes, same pH. Okay, we check first we measure the effective surface charge. Okay, and as we expect, the ones functionalized with azide groups are more have a higher effective surface charge, and then we will come to the lab. Ramon went to the lab, measured the temperature dependence of the Brownian velocity, get different the same bilinear behavior but different crossover temperatures, and then we put these crossover temperatures in that master curves. Okay, and the results are quite nice. Okay, so we think that we can reconciliate this divergence between Aveiro and Madrid. We can reconciliate it using a new descriptor for that. Okay, so take a message. Okay, this is I prepared this supposing that Danny was here. Okay, but unfortunately Danny was not here. So, but I decided to I asked him a permission to do this. Okay, let's go back to shift 2070. Okay, and recover one of the Danny first slides in his lecture there. Okay, this is a picture of Danny from the dinner of this conference, and this is the slide of Danny. You see. So I was, this is me when I have more hair. Okay, and look. So, yeah. Why? Why it comes? Because in my talk, and I copy here part of the conclusions, I said that I talked about luminescent thermometry, okay? 8 years ago, I mentioned that to become a consolidated subject and not a temporary fashion, we need to diversify the research, okay, and demonstrate to other communities how important could be the method for their problems, okay? And then, look, today, 8 years later, I've shown how luminescence thermometry can reveal or can help to reveal water density fluctuations. Okay? It's a possibility that was far, completely far from my mind back in 2007 and probably far from anyone in the field at that time. So I began with the story of two young fish. We didn't know what water was. For them, water was too obvious to notice. And this is exactly what happens for us as scientists. The risk is similar, to overlook the most familiar substance of all. Okay? We are water, as we already saw during this conference. Okay, so what we have seen today is that water density fluctuations are not just random noise. Okay, they are the fingerprints of deeper organization. And so perhaps the real lesson, so my take-home message is this. The simplest question, what is water, remains the deepest one. Okay, and then more closely we look, the more we realize that the medium we take for granted is still full of discoveries waiting to be made. And I hope that luminescence material, luminescence thermometry could help this. Okay, acknowledgement. Some people that help us a lot during these years on thinking on this subject, the financing sources, but also I want to, as I am the last speaker of this conference, of course, I want to acknowledge the guy that put this together, okay? Remember, 8 years ago, Jorge, you start this conference, you put this conference on the map, okay? Now SHIFT is one of the most important conference on the subject combining energy and biology. Okay, so we are, I think that I can speak in name of all the community, we are grateful to you to put this together. And then yesterday, I and Carlos Bridge, we asked our friend, ChatGPT, which is a very close friend, we asked it about SHIFT and about you, okay? And fantastic! You see, we upload 3 pictures of George in 2070. Look, very young, 8 years ago, okay? And then this picture was taken during the music and talks event. Okay, so George, thank you so much for putting this together. Thank you. Thank you.
Thank you, Luis, for the very interesting talk showing how luminescence thermometry can impact other fields, how we can use it as a tool to make discoveries in other fields. I think that's critically important. Like usual, I'm taking over from Danny. He starts something, and I have to finish it. Questions? Do we have another microphone?
Hello, Professor. Thank you so much for your presentation. It was amazing talk and a visual presentation. So I had a punctual question about all this amazing discovery with the properties of the water. Do you think that it's possible to congeniate or comply about the future, disease, in this case, punctual cancer? For example, in the cells, the water, it's confined. It's too complicated because with the motion of the proteins, of the rest of the cells, is too complicated. And if you set that high and lows because different state, maybe we can develop not only biomarkets I mean medicines that can impede the metastasis, for example, with the use of this property of the water in the light and high density. Thank you so much.
Very interesting question. Okay, I'm not expert on this, okay, but I read something on this subject, and in fact, there are evidences that inside cells, the water is not the same, okay? It depends on the organelle in which you are looking. It depends if there is a health cell or not a health one, okay? And there are some papers about this, some groups that study this, okay? So think if in fact the temperature plays a role on the unfolding of proteins that everybody knows, and if there is any connection with this, with the presence of these low density domains, so of course this description of the internal structure of water will be crucial for that.
Thank you.
Thank you very much, Luis.
Thank you.
Doing your presentation.
Thank you.
Always, you are spectacular yourself.
Thank you. Thank you.
Have you heard about the antifreeze proteins and antifreeze glycoproteins? These are proteins that have evolved in fishes living in the Arctic and the Antarctic seas. And because of fish are normally hyposmotic compared to the medium.
Yeah.
At the temperature they are, they should be frozen. But they are, of course, not. And a part of the strategy is the development of these proteins.
Yeah.
And they have some kind of trend to capture water molecules and to form a hydration shield around with a change in the free energy so that the crystals cannot be formed but remain attached to the proteins.
Yeah.
So the rest of the water is liquid in the cells, in the animals, but most of the crystals that will be formed are still these proteins. Yeah. I wonder whether this has something to do with these two domains you are talking about.
Yeah, so to be 100% honest, I don't know, okay? But yeah, if you believe in that description, okay, if people, because let me clear about one thing. People that work on this community, I am not working on that, but if you read the papers, they are not so friendly as the illuminations community here, okay? I do not have time to present here, but there is a paper on physics today, and the title of the paper is The War of Water. And very briefly, it was a huge discussion during a conference between two groups in such a way that the chair need to stop the section, otherwise the guys start to really physical aggression. Why? Because one believed in this two-state model and that the other one said that no, this is not, this is something that is not true. So answer your question. If you think that this mixture of these density regions are really present as the recent experimental results show, certainly there is a really influence.
Yeah. From the evolutionary point of view, because of, for these genes, I remember when I was a teacher at this university, is one of the genes that have more copies in the genome of these animals. And there's something like 40 to 50 copies of these, in particular these antifreeze glycoproteins. Yeah. They have a great affinity for the water molecules because they have plenty of threonine residues, which, as you know, they are hydroxylated and they have a trend to bind to water.
Yeah. We should take a look on that. Thank you.
Get back to the lab on Monday. So I don't remember who had their hands up, so I'm just going to hold my hand here.
Thank you, Louis, for a brilliant talk.
Thank you, Andrew.
And really nice science.
Thank you.
Also, really a big relief to find out that we can still trust both Madrid and Aveiro results.
Yeah, no, this is one of my major concerns, okay? Imagine, look the Danny faces, okay?
But my question,
Yeah.
it's always nice to see heavy water as a comparison, but I also noticed that both below and above TC, the slope in heavy water was steeper than in normal water.
Yeah.
Why?
Very good question. And we don't know why, okay? But this is the first point. But then we think on that and we decide to use water in which oxygen is replaced by an isotope. Okay, so we have water in this side, heavy water in that, but in between we can use water with an isotope, and the results are very interesting. Why? Because TC belongs in the middle, so it means that, when we change TC, it means that we are changing the relative proportion of low density and high density domains. And there is also changes on the slope. So, and we believe that the slope is related with the facility of the probe move along of the dispersion. Okay, so we are analyzing this data. So I hope that, I'm not sure if we will be able to have an answer for you, but at least new results certainly will come on that.
Thank you.
But thank you for this point.
Okay. There's a lot of questions here. Hold on.
Thanks for the nice talk.
Thank you.
So light excitation should also be able to change surface density for if you have a semiconducting probe, and I noticed some of these were semiconducting. So first, do you think that those results were perturbed by the change in surface density from the excitation? And if not, could you actually do some dynamic changes in these properties by doing excitation?
To answer very clear to your point, excitation is really crucial. So we should use low laser power density. Okay, why? Because 980 also heats water, so we need to take this into account, and we use an excitation. This is why it is important to have the best nanoparticles. We are discussing on this today. Best here means that the absorption cross-section should be enough to have a nice signal-to-noise ratio, okay? In order to use low laser power density to increase the temperature of the water below the uncertainty of our method to determine the temperature. Okay, we are on this situation. But if you change the laser power density, if you move from a continuous excitation to a pulsed one, you will have new information. Okay, but we still be on this very narrow range of excitations. Okay, low laser power density and continuous one.
Okay, a beautiful talk and brilliant results. Congratulations a lot. Now, related to what Andres asked and what you also answered, can you correlate that slope that you observe in heavy water and normal water to the hydrogen bonding strength in heavy water and maybe a kinetic isotope effect? Is there a correlation? Have you checked into this?
Yes, I hope so. Okay, but okay, I will disclose a little bit our results that you can also see in this paper that is now under discussion in Journal of Chemical Physics letter. Our idea after showing that master curve is that can we estimate the proportion of low density domains in that hydration shell? Because if you look into the literature, the results are amazing. So there are groups that propose 30%. Other groups propose it 1%. So it's a huge interval. So this was our efforts, okay? We focus our efforts on using our results to estimate the amount of low density domains that we have in this hydration shell. But yeah, we need to move for a more detailed analysis of the slopes, because the slopes also depends on the size and on the pH. And now at that time it makes us a little bit, you know, it is not easy to try to figure out that two dependence. But now with this new description, so maybe we can go further on this. I hope so.
Thank you, Luis, for the great talk. At the very beginning, you showed a phase diagram. I'm wondering whether luminescence thermometry could allow you to explore more of the phase diagram and maybe answer some questions.
Yeah, very good question. Very good, Philip. Because you see, I will not go back to show the phase diagram, but if you move along of the pressure axis, okay? Because we are at ambient pressure, but if you move along the pressure axis, we expect to have changes on this crossover temperature, okay? And then we can, because if you look to this diagram, okay, and it is a very funny story, because I want to know how the authors designed this phase diagram. And then I asked Ramon or Fernando, I think it was Fernando at that time, because I think that it is more the probability of getting an answer if you wrote saying that I am a PhD student and I am struggling with your results, can you please? And then we realized that there is a part of that diagram which is speculation, okay? And that part is exactly how TC depends on pressure, okay? And then we are in cooperation with Madrid after we, you know, come back friends again. we are thinking in performing these experiences, okay? Try to change the pressure because they have equipment for that, and see if we can, with luminescence thermometry or even with optical tweezers, to check this.
Last question, and then we have to get on with the award ceremonies. If you have questions, I'm sure Luis will be happy to answer.
Yeah, for sure.
I'll make it really fast as well. Thank you, first of all, for making your talks always and your science always more and more interesting.
Oh, thank you.
So my question would be about the appearance and disappearance of these domains of a low density and high density water. Once you are at equilibrium and there is this a beautiful metaphor that you use to show this appearance and disappearance, is there any law that can simulate statistically how these domains change in time at the equilibrium?
Yeah. Okay. No. Yeah. The answer is relatively simple, because the people that perform simulations, they can say yes. The point is that the fight that I mentioned before is exactly between two groups performing simulations, okay? And then depending on the model that you use for describing water, okay, and not that aqueous suspension, because concerning this aqueous suspension of proteins or nanoparticles, there are very, very few works simulating the hydration water. But yes, certainly, depending on the model, you will get the numbers about the fluctuations between the two domains. What is not yet clear is the size of the domains, okay? This is also something, you know, not yet well established.
Thank you. Before I conclude this plenary, besides Luis's proficiencies in science and presenting, for many years we've been meeting at these conferences, he, I, others, and smoking cigars. And discussing all of life's problems and likely solving most of them, at least until the cigar ends.
For sure.
So we formalized this group last night and we voted. We made him the president of the Rare Earth Cigar Club. So please join me in thanking Luis. Thank you. And thank you to all the plenary speakers of this symposium.